For example, everything comes under what is known as statistics, okay, for which probability is a primary tool. Okay, so now what do you do in statistics? If you look at classical statistics, for example, you have some random data. So you want to model this data. For example, you assume that it comes under from, it is drawn from a class of distribution, let's say Gaussian with certain mean theta, and you are supposed to find theta, right? This is called an estimation problem. Or you are given these samples, it will either come from, let's say, P0, for example, Gaussian with zero mean, or P1, okay, Gaussian with mean mu. And you know both, you know the mean mu, okay, so you know both P0 and P1. Now you are supposed to classify or detect, or this is called the hypothesis testing problem. Okay, is that fine, everyone? So people have studied this in a, there are books and thousands of papers written on it, right from, let's say, 1900s till now. Okay, even now people study something similar to this. Okay, now what happened over the years is that um, in statistics, generally people assume that you know this class of family of distributions, or you know P0, P1, etc. Right? What happened was, when people started looking at, when they started collecting a lot of data electronically, and also the advent of neural network, they saw some patterns in the data. Okay, for example, you can extract certain. I don't know how many of you know, have some background in machine learning. No one? Rishabh?
Sir, I have, sir.
You have, right?
No,
So
sir.
I won't go into the details of it in this class, because let's not waste today's class
Sir,
time. So yes,
sir, maybe in the next semester, we will be having some machine learning course.
yeah, yeah, you will. So what I will do is I'll point you to the set of a couple of lectures that I gave as part of mathematics for data science course, which talks about basics of machine learning. So what is the motivation? What do you mean by neural network? Very intuitive, high level, and you will see what is the difference. Okay, but it comes under statistics. Okay, so it's a, see, people who used to do statistics, they call it machine learning just to market themselves in some sense. Okay, that's what people are doing. Of course, there are certain challenges in machine learning. For example, if you look at deep neural network, the biggest problem there is optimization, right? How do you find the best neural network or neural network weights? So there are very fundamental questions that one can ask, unlike classical statistics. But still, in summary, I would call machine learning a part of statistics, okay, or probability theory. Okay, so anyway, let's not. So, for example, if you don't know the distribution P0, P1, okay, you don't know the distribution, you don't know the class of distributions. So, what do you do now, right? What you do is you just look at the pattern. For example, one set of data points lie here, and other set of points lie here, and you just know that you put a plane here and say if it is to the left, it is one part H0, if it is right, H1, H0 and H1 are the two hypotheses, right? So how do you learn this plane is the question that you ask in neural network. Okay. Anyway, so this is what you do. So as far as MDP is concerned, there are any questions, the framework, etc. Yes. Any questions? Whatever I have done so far, right? Yes. Any questions?
So this part is clear.
Okay.
And
So
the algorithm implementation, that is,
which
uh,
algorithm implementation? Huh?
so like some iterative implementation. You
So
given
I'll
the
come
next.
to that. I want to just generalize. So essentially, what we did was we wrote what is known as the value Bellman equation, right? So we wrote Bellman equation for finite time, right? That's what we did in the last class, right? As so Vn, the value, at time n was a function of Vn minus 1 and so on, right? That's what we did. So now let's generalize this to an infinite time, right? So we looked at two kinds of problems: maximize the reward over finite horizon, maximize the reward for infinite horizon, right? Let's look at the second option now. What is it that we are going to do? So let me make it slightly more formal now. I think you might have seen some of these, but it's slightly more formal. Okay. So now, as usual, you have these things. Okay. So set of states, typically finite. Okay. You have set of actions. For example, in communication, set of actions could be transmit or not transmit, or transmitted power P0 or P1 or P2 and so on, Pn. Okay, n levels. Okay, and you have a transition probability, that is probability that you go to a state S dash given that you were in state S and you take an action A, right? This is what it is. In fact, this is equal to, if you look at the time notion, right? Why is this Markov decision? So this is a Markov process, meaning the state that you are going to be in at time t plus 1. Okay, so how am I going to write this? So okay, so x, I'll write it as the Markov chain as x1 x2 x3. So this will be xt plus 1. You are in S dash, given xt you are in st, and action at time t. Okay, so I'll call it as at. You take a xt minus 1, you were in state st minus 1, and the action that you took was, let's say, at minus 1, and so on. At time 0 you were in S0, this is called the initial state, and at time 0 you took an action A0. Okay, so this is the conditional probability that you should be looking at in general. But if it is Markovian, this turns out to be simply xt plus 1 time you are in state S dash. The probability of that only depends on the current state and the current action. Okay, nothing else. So this is regardless of what happened before. Okay, regardless of st minus 1 etc. is 0, and for every action that you took before, doesn't matter what happened. Okay, this is Markovian. And the third thing is even the reward, right? So the reward, you have this, the reward that you get r dash, given that you are in state S and A, is described by this process. Okay, this is the probability with which you are going to get certain reward, given that you are in state S and took an action A. Okay, so now in finite time problems, it turns out that it's always better to take actions which depends on time. Okay, at this time, if you are in this state, then you probably have to take this particular action. If you are at time 0 and you are, say, at time 1 you are in some state, maybe you should take a different action as opposed to you being in some later time, right? So but it turns out that if you have a nice Markov chain, whatever nice means, I'll talk about that a little later. So it turns out that a policy which is a stationary policy, meaning the, okay, first of all, let's look at what is a policy, right? You have to take an action when you are in certain state, right? So that's what you have to do. Maybe you should take an action when you are in certain state, and you also have the time information. But in general, pi is, so policy is a mapping from the set of states to set of actions. Okay, is this fine? So this policy is called a stationary policy. Is this fine? So in other words, even before starting the game or the entire problem, you can figure out, given the transition probabilities, etc., you can figure out what this map should be, and you just keep on employing, right? So in fact, this is called a stationary. In fact, this is almost a deterministic policy, right? If you want to look at a random policy, then this policy pi maps the state to set of probability distribution on actions. Okay. Anyway, let's not worry about that here.
Hello, sir.
Yes.
So this pi is same for every state or like?
No. So for example, okay, example. Let's say you are in, you have two states, 0 or 1. An action could be transmit at medium power, transmit at low power, high power. Okay, then pi of 0 could be, well, I think in this case it's okay, I think I'll just take 2. Okay, transmit, don't transmit. Pi of 0 equal to 0, pi of 1 equal to 1 is one set of policy, right? The second set of policy could be pi of 0 is 1, pi of 0, pi of 1 is 0. Okay, these are the two possible policies that you can have, right? This is a stationary policy because it doesn't matter which time index you are looking at, whether you are taking this action today, tomorrow, or next year, right? It doesn't matter. If you are in state 0, you're going to take an action 0, not transmit. If you're in state 1, you're saying transmit. Is this fine?
Yes, sir.
Okay. Now,
So,
yes.
so is this the policy pi same as the one we used to describe as the distribution?
Which distribution are you talking about?
So in the like the Markovian chain stationary distribution, we used to say that pi p equals to pi, that pi only.
No, 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 no. Oh, okay. So, sorry. This is a map. Okay. Don't get confused with the stationary distribution pi. Good point. Okay. This is a caution. Good that you brought this up. So this pi is a map. It's a function. And the pi that we used earlier was for describing stationary distributions. The reason why I didn't change this pi was because people do use extensively use pi to denote the policy. So that's why I didn't change. Okay, if you look at any videos or any textbook, for them policy is denoted by pi. And similarly, the stationary probability in a Markov chain is also represented by pi. Okay, so keep that in mind, and I hope this is fine.
Hello, sir. One more thing.
Yes. Yes.
So the Markovian property that you mentioned, like the top of the screen, like probability of xt plus 1 equal to is that thing is same what we learned in Markov chain, right? I mean
correct. There is no, yes. So just to give you a very specific example, so state 0, state 1, there's a Markov chain. Okay, so some probability p, you are going here with probability 1 minus p. This is 1 minus q, and you are in this 1 minus q, and this describes the state, the evolution. So each time you are in some state, you are going to get reward. Okay, so the reward could be this. Okay, if you take action, so this reward, I'll write it like this. If you take action 0, reward could be 1 with probability of half, 1.5 with probability half. Okay, if you are going to take an action 1, for example, the reward could be, for example, 1.2 with probability 1 by 3, and maybe half with probability 2 by 3. Okay, this can be the specifications. And similarly, you have the same kind of a split here. Okay, so this is the kind of problems that we are looking at. Is that okay? Fine.
Yes, sir. Yeah.
Okay, so for example, if you are in state 1, that means the channel is good, right? You take an action not to transmit. That means if you don't transmit, you will get a reward of half, 1 with probability half, or 1.5 with probability half. So what does that mean? Maybe I have defined reward in such a way that even if the channel is good, it's very close to being bad, then the reward will be reasonably okay, because it's good not to transmit. Okay? And similar, whatever. So you can map the problem appropriately. Okay, is that fine? Anything else? So this is called a stationary, in fact, deterministic policy, right? These are all deterministic. That means before even starting this game or this process, if I give you this policy pi, I know that if you are in state 0, you have to take an action of 0, not transmit. If you are in state 1, you transmit. That's the idea, right? So what is a stochastic policy? Well, let me give you an example. Okay, so what is stochastic policy does? So if you are in state, okay, if you are in state 0, okay, what you do is, let's say with probability q, you transmit a equal to 0, a equal to 1, okay, you transmit. With probability 1 minus q, you back off, right? If you are in state 1, with probability, let's say alpha, you transmit. With probability 1 minus alpha, you don't transmit. Now, this is a stochastic policy, because even if you are in state 0, beforehand, you wouldn't know whether you're going to transmit or not. What I'm going to do is, if I'm in state 0, I'm going to take a coin with bias q, flip it. If it is head, I'm going to transmit. If it is tail, I'm not going to transmit. This is called a stochastic policy. So what is it doing? It's taking the states as input and giving probability distributions on the action as your output, right? So this will be, let me denote it by PA, okay? This is the probability distribution on action set. This will be your map, right? So this is called a stochastic policy. Is that fine? Is that okay? Fine, right?
Yes,
Any
sir.
questions so far? Sumit, Ayush, Praveen, Jayant?
So, sir, here policy means, sir, actually you are just defining a function,
It's
right,
a
sir?
function.
Yeah.
From an
So,
engineering viewpoint, it's some decision that you are going to take. So the function will tell me what is the decision based on the state.
sir, once we define one policy, suppose, sir, in that case, sir, everything has become deterministic. Then, like suppose, sir, in the previous example, if we just fix our policy to the first one, like pi of 0 is equal to 1 and
Hmm.
pi of 1 is equal to 0.
Yes.
Then, sir, in this case, is it deterministic? Like its policy is
Yeah, it's a
deterministic. If we
deterministic policy. Yes.
so, sir, so how the probability comes in between this, sir? Like it's from state this to going
No, no,
to
no.
another
So,
state.
okay. So, okay, this is the way you are going to take your decision. Okay. The way the nature is going to behave depends on what action you take and which state are you in. And then the nature will decide in a random fashion what to do. Right? For
Okay.
example, let's say you are in state 0 now. Okay.
Yes, sir.
You take an
Mhm.
action, let's say not to transmit. Right? Given those
Okay.
two, well, I think, okay, let me give you a very, very specific example. Okay. Again, state is 0, 1. Action is also 0, 1. Okay. Transmit, not transmit. This is the Markov chain. Okay. 0 is the state, and you decided not to transmit. Okay. Then this is Q. This is 1. Okay. Let's call it as Q0. And this is Q0. You go to state 0, and then if you decide not to transmit, then again you'll come back here with P0, and you stay back with probability. Sorry, did I make
So
a
it should
mistake?
be
Yeah,
state one, no?
it's state 1. You are right. State 1, and you decide not to transmit, then it will be 1 minus P0. This will
Yeah.
be okay. I'll just write it as 1 minus Q0, Q0. Okay. This is how it will evolve. Supposing you are in state 0, but you decide to transmit, then it might decide like this. Okay. Is this fine? This is
Yes,
how
sir.
the
Yeah.
nature is going to evolve. The way you take action, it could be either deterministic, that is, you're going to fix it. So suppose I'm in state 0, I'm not going to transmit 0. If I'm in state 1, I'm going to transmit. Right? What will happen if that is the case? Suppose I am in state 0, I'm going to transmit, not transmit, right? And I'm in state 1, I'm going to transmit, right? So this will be Q0, 1 minus Q0. This will be P1, 1 minus P1, right? This is how it looks like. Do you agree? This is how it's going to
Yes.
evolve for your policy, right? For
Yes.
this, there could be a reward, right? So reward being here, right? Now I'm going to collect these rewards and look at the average. for this. And similarly, I'm going to look at, this is an easy problem, right? So 0 transmit, 0 1 transmit. There is some Markov chain for this. Again, there could be another which is like 0, all possible combinations. So essentially, if I want to write it like this, right, 0 0 1 0. Okay, so basically you have this being 0 and this being 1, right? So this could be 0 0 1 1, right? This could be 0 1 and 1 0. This could be 0 1 and 1 1, right? These are the 4 possible Markov chains depending on what policy you want to employ. Now for each of these Markov chains, you'll have some average rewards. So now you have to pick the policy that maximizes. For example, this hopefully this policy maximizes the average reward, then you're going to not transmit when it is 0, transmit when it is not when it is non-zero. Okay.
Okay, so we have to maximize over the all possible function from the states to the so
Exactly, right? It's a
Excellent, sir,
very
yeah.
seemingly very complicated problem. So you have to
yeah, yes,
choose a map that goes from
yes, sir.
states to action, and you have to pick the best map. That's the problem, right?
Yes, so in practically, sir, it is, I think, is there any
Okay.
algorithm to
That's
find
what
such
we
a
are
thing, sir?
going. That's what we are going to do now. Okay. We
Okay,
did
sir.
partially for finite, but let me rephrase it
Yes,
for
suppose, sir, in
infinite.
finite case, sir, it will be a lot, means huge.
Meaning?
Like, sir, suppose our states are infinite and then actions are also infinite or maybe finite action, then still we get means uncountable number of policies. So
For
from there,
no,
sir,
the number of policies depends on the action space in the state space, right?
yes, sir, yeah, state space is finite, suppose, sir, infinite. If
Infinite, then you definitely again, yeah, you'll definitely have infinite actions
yes, sir.
possible, right? Infinite policies possible.
Yeah,
Actions
yes,
could
sir.
be finite, but there could be infinite policies possible, right?
Yes, sir. So then from there we have to find maximum one. So
Yes, right. So
this,
let's see what does that amounts to. Okay.
okay, sir.
Hello,
Fine. Yes.
sorry, you are saying that here we have to pick the maximum one, like something that maximizes.
Yes. Yes.
So what are we going to maximize actually?
The reward, right? So for example, see, you take this Markov chain, right? Suppose you have chosen to transmit when the state is 0, again transmit when state is 1. Okay, your policy is this: pi of 0 equal to pi of 1 equal to 1. Okay, this is your policy. This is the stationary deterministic policy that you have chosen, right? Now, being in this state, the nature will choose some reward. Okay, so let me call this as R01, and this reward is R11, right? So now, what is the average reward you are going to get? Assuming that you are starting here, okay, S0 is 0. So what is the reward? You get R01, that is the initial reward that you get, times with probability Q1, you are going to go here and get R11 with probability whatever. So you have to compute the average reward here, right? So you are going to switch back and forth between R01 and R11. For example, if Q1 and P1 are equal to half, then the reward would be simply by symmetry, it's R11 by 2, right? That will be your average reward, long-term average. Is that fine?
Yes, sir.
Okay. Yeah. So that's what happens. Half the time you are going to spend in state 0, in which case you will get R01 as the reward. Half the time you are going to spend in state 1, in which case you will get R11 as the reward. So the average reward will be the sum by 2. Okay, it's as simple as that. But in general, you have to compute what is the average reward. Okay, is that fine? Okay, now, yes. So basically, this is as far as the deterministic policy is concerned. So what is random policy? You understood, right? It has to map to the probabilities, the coin. Okay. So now, what is a reward? A reward is essentially a mapping from state action pair to a real number, right? So this is how I can define a reward. Okay. So reward is a mapping from state action to a real number. Okay. So it will tell me what is the reward that you have got. Okay. Now let's look at infinite horizon problem. Uh, this would be the infinite horizon, right? So for example, rate at time, let's say t plus tau. So at time t plus tau, you are in state st plus tau, and you are following a policy pi, which is of course a map of st plus tau, right? So this is state, this is action, because pi maps states to action. So pi of s is the action. This is the reward that you get, right? Of course, ideally I have to do the following, right? Tau equal to 0. That means you start from time t to tau t minus tau. Well, I'll just use infinity here, okay? That means it's an infinite reward, infinite some reward starting from time t, okay? But generally this could be infinity. What we can do is we can multiply this by gamma tau and assume that this is between 0 and 1, okay? This is called the discounted reward. Okay, this is called the discounted reward. Is that fine? Is that okay?
Yes, sir.
Okay.
So it will just bring the sum to the finite, I think, no, sir?
Yeah, that's what it does. For example, if your reward is bounded by m, let's say the maximum reward
Yes.
that you get is, let's say, 10, right? Then
Yes,
this
sir.
can be at most what? Less than or equal to 10 times summation tau equal to 0 to infinity, which is 10 by 1 minus mu, right?
Yes.
So which is always finite, as long as, of course, gamma is nu is less than 1. So this is always finite, right? So you get a finite number.
Yes, sir.
Otherwise, the problem itself does not make sense. Now what you do, of course, you should, this is the sum, but you have to take the average, right? You take the expected value conditioned on the fact that at time t, when you start, you are in some state s. Sorry about this, I don't know, something happened.
Hello, sir.
Yes.
Sir, the
Yes, yes.
reward that you defined above, sir.
Huh.
How is that random, sir? That
Which
mapping.
reward?
R.
Okay, so well, this is, of course, whatever I have shown is perhaps a deterministic reward. Okay, so it's deterministic reward.
Sir, this is the
But in
definition of random variable.
which one is the definition of a random variable?
Sir, R from S cross S space
No,
to
no, no, no,
real
no,
number.
no, 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 no. So what I'm saying is this is deterministic. You give a state and an action, you know the reward. For example, if you can measure the distance very accurately, in the robot example, you are in some location which you know exactly, that's the state, and you take an action. For example, you say move to the right by half a meter, then you move to the right, then you exactly know the distance, so you know the reward exactly, right? There is no randomness there. If there is some measurement noise and all that, and there could be some randomness. Okay, so of course, if it is random, you cannot basically write like this, the mapping from state cross A to the number. Okay, is that okay?
Yes, sir. Sir, one more thing, sir. Why is it called discounted, sir?
Discounted because what is happening is you're multiplying it by gamma per tau, right? So that sort of discounts what happens in the future. I mean, it gives lesser and lesser weightage for what is happening for large taus. It's discounted, right? You are basically disregarding all the gain that you get. Okay, is that fine? I think okay. So I was writing this. Given the state at time t, st is s. Okay, this is the average reward that we would like to look at. Okay, so before moving further, so what is the difference between this and the problem that we looked at in the last class? The last class was finite horizon, meaning finite time, and we wrote an equation which is like this, right? V at time n star was max over all actions, r action plus we wrote this as some P for taking action A, right, times V n minus 1 star, right? Do you agree? This is
Sir?
what we looked at, huh?
The reward is deterministic, no, sir. Why should we take expectation of that, sir?
So the reward is not deterministic. So this particular map, I mean, okay, so if it's confusing, then maybe discard this, okay? Don't worry about this. This defines a deterministic reward. In general, the rewards can be random, right? For example, I can give you an example, okay? So let's say advertisement posting, okay? Take that example. So you have a web page or you have your Facebook page, and I want to put an advertisement on it, right? So if I put putting an advertisement is an action that I take, right? So you are in some state, meaning you would have clicked on a few advertisements before, okay? Those are all being in different states. So now I put an advertisement. Do I know beforehand the reward? That means, do I know beforehand that you're going to click that particular thing for sure?
No, sir.
No, right? You are going to click with certain probability, or you're not going to click with probability 1 minus that, right? So that is a random reward that I get. Is that fine? Is that okay?
Yes, sir.
Yeah. So this is a case where you are doing this iteratively. Can somebody tell me what this resembles? Okay, Ayush, maybe you have taken speech processing, right? You would have seen something similar to this, right?
Yes, sir.
What is this?
Sir, I think we used to do this in Viterbi algorithm.
Exactly, right? So it leads to Viterbi, right? So if it is finite, you can do Viterbi sort of thing. Okay, I'll leave it as an exercise. You just read through, or in general, it's dynamic programming, right? Right? That's what boils down to the previous class. Now, if you're looking at infinite horizon, it's not so straightforward, right? I mean, not well. Viterbi is not straightforward, by the way. It's quite complicated. Okay, so I encourage you guys to look at what is Viterbi. Okay, now let's look at what is Bellman now for this our case. So what do you think is Bellman for our case? So first of all, we need to look at what is the so let me call this discounted reward as the value that you get, V, okay? Being in state S, that means you start in state S, follow the policy pi, right? Pi will tell me what to map, right? So if you are in some state, it will tell me what the action to take. So pi is the policy that you are going to follow. Being in state S, then V pi of S is the expected discounted reward that you get, okay? Now let's look at what does it result in. Okay, so let's look at the V pi of S. This is nothing but expected value of, I'll rewrite this, summation tau equal to 0 to infinity in general, mu tau times the reward, right? Reward of st plus tau, and then pi of st plus tau given st, right, is S. This is what we get. Okay, now at tau equal to 0, what do we get? It's st comma pi of st, right? So it will be expected value of r of st comma pi of st, given that st equal to S. Okay, this is what we get. Plus, what is the second term? So second term would be expected value of summation tau equal to 1 to infinity mu power tau r of this thing given st equal to S. Do you agree with this step? Okay, now given st is equal to S, I can substitute st here, right? S in place of st. This is the pi of S. Now S and pi of S, so it's independent of what happened at ST. So this is the average, right? Okay, this is the average reward that you get. Being in some state, the reward is independent of what happened before, and of course, I have condition on S, you have this reward. Okay, now ST equal to 1 to infinity. So if I were to change this, I can do the following, right? I want to change it to 0 to infinity again. What should I do? I should change tau to tau plus 1, right? That means we'll have tau here and we'll have a gamma outside also, right? This is the expected value of this times. What is the reward? Reward of S t plus tau, but t plus 1 plus tau is what we have. Pi of S t plus 1 plus tau is what we have. Given St equal to S. Is that fine? Is that fine, everyone? Is that okay? Okay. So what is it that I can write here? Next step. Excuse me. This is expected value of R of S comma pi of S. This is the average plus nu times. Okay. So what can I say about this? So nu power tau times, I have expected value of the reward given St is equal to S. So what is it that I can do? See, this is at time t, right? This is at time t plus 1, of course, slightly in the future. So now how do I write this particular expression is the question, right? So what do you do? What is it? Sorry, what is it that you will do? See, are you guys there?
Yes, sir. Yeah.
Okay. Any question so far? Yes or no? Any questions? No?
No, sir.
See, what is
Actually,
this?
sir, here what you have done, sir, it just it was summation from 1 tau is equal to 1 to infinity. So we just shifted one
Exactly.
place back, like
That's all. That's all.
0 to infinity.
Substitution. That's all. Yes. Okay. So now instead of st, you have st plus 1. So at time t, you are in S, right? At time t plus 1, you are in S of t plus 1 plus tau, right? That's what we have. Now in between, so there could be several states that you can reach, right? And then from there you can go to this particular state. So the question is, how do you write that? Right? So I can go to any state in between S dash, right? From S dash I can go to, from S I can go to S dash, from S dash I can go to whatever, the future. Do you agree?
The same like we did in Markov chain also.
Exactly. So this is indeed a Markov chain, right? There's no difference, right? So now, sorry, this is not gamma per tau. This is nu, right? Nu, what is it that I can do? I can write this as, okay, so let me write this and then ask you why this is true. So the probability of you being in S dash, given that you started in S and you took a policy pi of S, from there your value would be this. Do you agree with this iteration? What is it that I'm doing here?
So this is just like Markov chain with added extra reward. The reward thing was not there in Markov chain.
Exactly. So there is no, I'm not doing anything big here. I'm just applying those, whatever we have learned in Markov chains to this particular scenario. The only extra thing, as you rightly pointed out, is the reward. That's all. I'm just putting the reward that you get. Why is this true? Next step. From here to here. see what is it that I'm doing. So I'm looking at the reward, the future, the sum of the c. For example, tau equal to 0, you'll have t plus 1, right? The next one. So t plus 1 could be any s dash. Do you agree?
Yes, sir.
Right? So that's what I'm doing, s dash. Given that you are in state s and pi of s was your policy. Now you go to s dash. The moment you go to s dash, what is the average value that you get? Pi v pi of s dash, right? That's what you are getting here, right? This is the discounted reward for you starting in s, going to state s plus t plus s plus 1 plus tau in t plus 1 step, and subsequently go to some other whatever it evolves. Is this fine? Is that fine? No questions? Hmm?
So this is like this counts everything like infinite state problem also.
Yes. So um, um, I'm not restricting on anything, right? The
Because
only
tau
thing that
runs plus
I'm
infinity.
restricting is s dash is countable, meaning the number of states is countable, can be infinity. Okay.
Okay.
Yeah. So I'm not restricting on anything. Okay. In fact, even if it is continuous, this integral will become this summation will become integral, right? To that extent, we have replaced. So what was this? This was v pi of s, right? V pi of s is some number plus nu times summation over all s dash some probability times v pi of s dash, right? Is that fine? Okay. Is that fine? Okay. Now the above can be written in the following way, right? As we did in the finite case. I'll write v pi of s for each s. I'll stack it in a row or a column, and I'll call that as v pi. Okay.
Sir, this S is like different. V pi for S is different for different S, right?
What were v pi of s is different for different s. Yes.
Okay.
So if s is, for example, 0, 1, 2, 3, 4, okay, finite case, I can write v pi of 0, v pi of 1, v pi of 2, and v pi of 3, and v pi of 4. Stack it one after the other and get a column vector, right? So that is v pi. If you have infinitely many of them, you have an infinite by one column vector. That's all. Okay. And similarly, expected value of r of s comma pi of s, the first column, I can write it as r. Okay. Well, again, it also depends on pi. Okay, maybe if you want dependency, I'll write it. Nu times, what will happen to this? This is a transition probability matrix, right? I'll call it as P. Okay. So maybe I'll write it as P pi or something. Again, V pi. Right? This is what we get. Do you agree? Everyone?
Sir,
So mu
Yes.
will be transpose.
Huh?
Mu transpose.
New transpose. Why? New is a number. It's new
Okay.
power t, right? New power t. So new is a number.
Okay.
Yes. Yes. Who was it? Ravi?
sir,
Yes.
sir, this is for particular policy pi, no, sir. There can be
Yes.
many policies.
Yes. Right. You have to look at which policy will give me the maximum value, right? So essentially, I'm converting this whatever the policy, the actions that you take into a number which will dictate which will indicate what is the reward that you get. That's all I'm doing here. So that's why it's called the value. Okay.
Means, sir, for each iteration, sir,
Uh-huh.
I will compute v of y for different policies. Then
Hmm.
is it like that, sir? Means I will see the best policy and choose that best policy.
That's what you have to do, right? So if you knew this equation, right, perhaps you can find for each pi, you see what is v pi and pick the best. That's all you can do. Okay. See, for each pi, if you can solve this equation, I'll get v pi, right? So let's see what is the solution of this. Let's look at, if it is finite, then it's very easy, right? So what do you get? You get v pi times identity minus nu times p pi, right? Sorry, is this correct? No, this is to the right, which is equal to r pi. So whatever, I'll write it in quotes because I haven't proved it. So we will prove it now. This is what? identity minus nu p pi inverse r pi. This is the solution provided the inverse exists, right? Is that okay? Now what happens? Suppose this is true. If I know p pi r pi, I have to keep on choosing different pi's and see what will be v pi. So pick the one that gives me maximum, right? That's what we have. Okay, is that fine? Well, especially we should look at v pi of s that gives me maximum, meaning you look at the sth row of v pi and keep on changing pi and see which pi will result in the maximum s whatever row s, right? Is that okay, everyone? Yes or no? Rishabh?
Yes, sir. Yes.
Yes, Ayush?
Yes, sir.
Yeah.
Sir,
Sumit?
sir, here the V pi you are calculating, no, sir, it is for a particular state. I mean, like at S only.
Yes, so
Means
it's
for
for a
every state we have to, sir, calculate for every policy. Then, sir,
okay, so
on
this is given, right? This is given to you. So you start in some state.
oh
You know that robot is going to start somewhere, right? So you know that
oh
state,
then yeah,
initial
yeah.
state, and then see what happens over time. That value will be v pi of s if you follow the policy pi. The
Okay,
only
sir.
thing is
Okay.
pi here. That's the issue. Okay.
Yes, sir.
Okay. Any other questions, Jayant?
No, sir.
Okay.
Sir,
Now, yes.
this would be very high value, no, sir? Means it will be
Why?
always bounded, sir. V pi.
Yes, right. So that's what we saw. So for example, v
Means,
pi.
sir, inverse will be.
No, you see, v pi is this, right? For example, if the reward is bounded, right, by m, let's say 10, right? You cannot you cannot earn anything more than 10. The minimum value is 0, let's say. Then this reward cannot be more than 10 by gamma 1 minus gamma, right? If gamma is half, for example, it will be 10 by half, which is 20. So the maximum v pi that you can get, regardless of what state you are in, is 20, right? That will be the maximum. Okay, is that fine? So now we need to prove that this inverse exists, right? Need to prove that I minus nu p pi inverse exists. Okay, this is what we need to prove, right? So now how do you prove this? How do you prove this?
Sir, maybe determinant not equal to 0 and spread it out.
Well, what is the determinant of, let's say, an infinite matrix, for example?
Sir, it would be better if you
Well,
can show that
if
its
you look
eigenvalue or
at
not.
finite also, yeah, deterministic determinant is one, but you cannot. Is there any other way? Suppose, okay, let's look at this. This is I minus A inverse exists if I can show, for example, the infinity norm of this is less than 1, right? Is that fine?
Yes, sir. Yeah.
Do you agree?
Yes, sir. Yeah.
So why is that?
Actually, sir, I just read this.
Well,
Actually,
okay, so now what does this
sir,
mean?
if we expand, sir, we
If
just
the infinity norm of A is less than 1, what does that mean? That means, hey, guys who are
Maximum value.
taking linear algebra, you should answer. If the infinity, so what is the matrix P that we are looking at? All the entries are between 0 and 1 because it's a probability transition matrix, right? Do you agree? And it's a stochastic matrix. Therefore, if you sum, for example, the rows, right, it will be 1. Do you agree? Right? So it's a stochastic matrix. Now I am saying the infinity norm of that stochastic matrix is less than 1. What does that mean? Entries belonging to 0, 1. Okay, that means the eigenvalues is, right, all less than 1. Do you agree? Therefore, it is invertible. Do you agree? So see this as a homework. Take this as a homework. It's important. So now let's look at what is infinity norm of. Maybe if you are not clear, I'll come back to this in the next class. So what is the infinity norm of P? Hmm? What do you think is the infinity norm of P?
Maximum of the components.
Yeah. So essentially, I can write the. So what will happen to the infinity norm of P? So this P it's the infinity norm of the P matrix, right? So if it's a vector, it's the sup norm. Basically, you look at the supremum of all the components, right? The absolute value of the components. Do you agree? If it's a matrix, what is the infinite sup norm?
Sir, it is the maximum of the row sum, right, sir?
Yeah, it's the maximum
Maximum
of
of the row sum.
right? Max overall, let's say S, right? The row sum, let's call it as S dash of this, let's say the SS dash entry. Absolute value is not required, but I'll keep it. So this is nothing but what? Max overall S, summation overall S dash, probability of S dash given S comma phi of S, right? So this probability is what? Is 1, right? Because summation overall S dash P S dash given S phi of S
Yes,
is
sir.
1. So the max is 1. So this implies nu times P infinity is equal to nu, which is less than 1. So
That's the one.
this implies identity minus nu times P is inverse exists, right? This is the idea. Okay. Okay. So there might be a few gaps here, but you should figure out what, I mean, from basic linear algebra, right? This is fine, right? The infinity norm is less than 1. Well, if you look at the infinity norm, it's essentially the max of the sum, right? The sum of the rows, right? That means this all the sum of the row, all the sums should be less than 1, right? That's what it's saying. So if all the sums are less than 1, what can is, how many of you have heard of Greshgorin's this?
Yes, sir. It is just coming from that also. That only.
Yeah,
Norm is
right.
less than one means all these eigenvalue will lie on the circle of radius less than one.
Exactly, right. So how many of you have heard of this thing, Greshgorin this theorem, or Rishabh, you have heard of it or no?
No, sir.
No, I think it's important. You just go through it once. Ayush,
No, sir.
no. Okay.
I think
Praveen,
the name was
it's Greshgorin. Okay, so I will write it. Is that correct, Sumit? I think so. I don't know if
Yes,
it's
sir.
Gorin or Gorin. Just look at that. So it follows from that. So don't worry. I mean, if you don't know this, it's perfectly fine. All that we have done is we have proved that the inverse exists. Therefore, I can find the value, right? And therefore, I can hope to solve the problem if I know everything, right? All the transition probabilities, everything. Okay. In the next class, what we will do is we will see that the value iteration actually converges. Okay. I thought I'll do it today, but couldn't manage to finish it. And then we will look at that. Essentially, we'll propose what is value iteration, and then we'll propose what is known as policy iteration, and show that policy iteration converges faster than the value iteration. Okay. If time permits, then we will look at maybe the Q learning or whatever TD lambda algorithms and all that. Okay. If time permits, otherwise I'll leave it as a reading exercise. Okay, I'll stop here. Any questions?
No, sir.
No?
No, sir.
Ayush?
no, sir.
Okay. Praveen? Jayant?
No, sir.
Jayant?
Sir, you mentioned about hypothesis testing, no, sir?
Mm-hmm.
It means different algorithms in machine learning. All those are one hypothesis, no, sir? Means each one is an hypothesis, sir.
No, see, I give you, let's say, an image. You have to say whether the cat is there in the image or not, right? That's a hypothesis testing. You say a cat is there or not there. H0, H1, H0, right? That's all.
Okay, sir.
That's called hypothesis, right? So that's called hypothesis testing. Okay. So classification exactly does that, right? It says it classifies, right? But typically you don't know the distributions there in classification problems. That's what you learn in your PRML, whatever, right? Pattern recognition and machine learning. So you recognize the patterns, and based on the pattern, you solve the hypothesis testing problem. Instead of using the probabilities itself to solve the problem. You don't know the probabilities, right? You try to learn the pattern. If you know the probabilities, you already know the pattern. Therefore, there's nothing. Well, it's interesting, but yeah, people have solved that problem, those problems.
Okay, sir.
Okay. Yeah. Any other questions? If not, I'll stop, and then next class, that is on Wednesday. So we have 2 more classes left, right? 2 or 3 more classes.
Hello, sir.
Yes.
Sir, when will be the end exam?
So maybe 1 second. Hold on. We'll fix that. How about 16th? Is that fine?
15th, sir.
16th.
Yes, yes. Because linear algebra it's on 18th.
18th.
Yes, sir.
Okay. 16th is fine, right?
Yes, sir.
Okay. Savan, just mark the calendar. 16th.
So this part is also included or not included?
Okay. So now, yeah, I was also thinking about that now. What do you think? Should I include this or not include this?
I think no, sir.
Huh? Why?
Sir, if included, what
So
type
say
of question will
20.
you ask from here?
Maybe I'll ask situation and ask you to model that as a MDP,
Sir,
right? Or a simple MDP and ask you to solve the problem. Yes, Jayant.
no, sir. For MDP, you can give like homework. We can practice, sir. That's not which is not evaluated. Only for MDP, sir.
Okay.
Sir,
Yes.
sir, on 15th we have data science according to like the academic calendar, academic timetable.
Correct.
So if it is 1 day, then how 16 we will do it?
Oh, yeah. So 15th evening, right? 15th is what? 1 second. Yeah. 15th is Tuesday. That's why. Yeah, it will be evening. So, okay, you want a 1 day break? Okay, then 17th. 17th is fine.
18th we have, okay.
Or see, anyway,
16th evening to 17th evening, sir.
yeah, that's what I'll do. 16th evening to 17th evening. Is that okay?
Yes, sir.
Okay, 16th again, but 16th evening I'll give, and I'll give enough time, okay, for you to finish. I'll keep in mind that you had just finished data science exam.
Okay.
Okay. Yeah. Okay. So, any other questions? If there are no questions, I'll stop here.
Okay, sir.
So
Okay.
what time to set the exam?
Maybe set it at 8 o'clock in the evening, because 7:30 to 7:30 is what I'm planning for data science. Okay, and the other 24 hours for this.
So
Let I take an hour break, for example, 8:30 or something, and then
Hello, sir.
yes.
Sir, can we keep that data science from morning to morning?
Yes, that will be much more like.
No, if everybody is fine, I have no problem. Hmm? Have to check. Hmm?
Yes.
Okay. Yeah. Okay.
Okay,
So
so
anyway, I'll give enough time. We will discuss. So somewhere on 16th, I'll start and end on 17th. Hmm?
okay, fine. So I'll just set the calendar event 16th 8 p.m. to 17th 8 p.m.
Uh,
Okay.
tentatively, but if we will see how the other course goes, and then we will
Okay, fine.
finalize this one. Okay. Is that okay, Rishabh?
Yes, sir.
Yes. You seem a little unhappy.
No, sir. No, actually, so we will manage, I think. But
Hey, you have to
morning
see.
for data science would be
I
better.
mean, we used to write back-to-back tests, man, final exams. And nobody used to care. Okay, I had an exam 2 hours before. So what? I cannot change that. That's what they used to say. But anyway, so since this was online and we hadn't declared the exams beforehand and all that, therefore I've been a
Sir,
little classification.
actually, things are like that 14 to 17, that 3 days we also have to give our seminar one day, I think.
Okay.
Sir, I think we will manage, yeah, we will see.
Okay, I'll see. Okay, so it will be on 16th or after 16th. Okay, let's decide on that. Huh? Prepare well before 16th so that you are ready for the exam.
Okay, sir,
Hmm?
okay,
Okay,
sure.
so we'll see. We'll look at all the possibilities and find a suitable time. As of now, Savan, you can play say at 16th evening, 8 o'clock, 8:30 to 17th evening, 8 o'clock. No, 16th evening, 8 o'clock to 17th evening, 8 o'clock. 8:30, sorry.
Okay, fine.
Yeah. As of now, we'll see how. Okay. Yeah.
Yeah, yeah.
Okay. Thank you. I'll stop here. Thanks. Bye.
Thank you, sir.
Bye.